Hey guys, how's it going? Welcome to another episode of Ferris Makes Demos. This is SNES Kefrens Bars 3. So on the last two demos episodes, which was last Sunday and the Monday right after, I started working on this Kefrens Bars effect after seeing a tiny intro that did the same thing. This called Super Keftendo. The thing looks pretty good, and I thought that basically the way that this effect normally works is you have the first row of pixels, and you basically trick the hardware into displaying that same row of pixels the entire way down the screen. Now, as it's being displayed, you draw, like each scan line, you draw an additional bar to those graphics, and then the ones that were drawn previously end up just getting stretched, and you get this effect. It's generally worked pretty well, except on this platform in particular. It turns out you can't really do that very easily at all. Because, or at least not in the same exact way, because you actually can't write to video RAM in any other point in the frame other than V blank, which is when the electron beam that scans your screen is going back up to the top of the screen, so you have a little bit of time at the end of the frame, or an F blank, which is where you basically force turn off the screen. And obviously we can't do that every scan line, so had to come up with a different way to do it. Now, I actually got in contact with the guy after having given this a couple attempts last weekend. I contacted the guy who wrote this, and seems like a nice guy. Basically was just super upfront about it. Was like, yeah, so actually the way I do it is he has the pixel data set up so that every pixel on the screen horizontally actually corresponds to a unique palette address. So he uses one of the graphics modes that gives him 8-bit color, and then each pixel can just display one palette entry the entire time. So that instead of drawing the bar data into the pixels data every scan line, he actually fills in some of the colors in the palette. So initially all the colors in the palette are black, and then he can fill in the colors as the thing scans down. And since you do have access to color RAM during H blank, that's actually possible. Now he doesn't actually do it with the SNES HDMA facilities, because it's a bit smaller to just wait for H blank and then actually fill in the bars there. And yeah, I think that makes a lot of sense. Another kind of funky thing that he did is this particular graphics mode that he's using is mode 7, which is the infamous mode on SNES, which will give you a 2x2 affine matrix that it'll translate the pixels with, so you can do some basic scaling and rotation in 2 dimensions. And what he does is it's actually more convenient to write out the tile data and the pixel data vertically rather than horizontally. So he actually does it vertically and then rotates using these mode 7 registers, so that ends up being on the top of the screen, and the rest of the effect works as expected. So I thought, since that was a lot simpler than I expected after having failed trying it initially, I thought I'd take this stream to actually do that. Just take the code that I've already written that sets up the HDMA and tries to write the pixel data into VRAM, and tweak that, and also tweak like the graphics mode we're using and everything, so that we can actually do more or less the same technique, except not with the sideways thing and using HDMA rather than waiting for H blank and drawing the pixels that way. So that's what I'm thinking. I think this will be kind of fun. So we can get started. By the way, hi to guys in the chat. I saw Local Hoster, Skeleton, Arthur Carlson, Evil, Love Like Semtex, Daniel Collin, W23, Metal Void, Zokwar, John Hunter. Lots of people in here today. Oh, shut up, Steam. Move some windows around here. And I'm totally having one of those weekends where one of the projects I'm working on, there's a part of it I just don't understand right now. So I'm a little frustrated by that. It's just made me tired all weekend trying to understand that. So a little scatterbrain, but that happens to me often, so. Yeah, good to see you here, by the way, Arthur Carlson. Just reading your comment here. Oh, one more thing. I'm pretty sure I fixed my connection issues. So we'll find out as the stream goes on. But basically, I'm pretty sure it was either a bad network adapter or bad drivers for the network adapter that I have, because it actually was only unstable on this machine. I noticed when it would crash pretty hard, it was only this machine that was affected. And my phone and my laptops and everything were still connected. So seems to be the point of failure there. And I went and picked up a cheapo Ethernet adapter that seems to be working great. So I did a stream test on Friday, and then, yeah, it's been going well. So yeah, we'll see. Oh, it is scatter in the brain. So basically where I left off was this. So this was basically we have these tiles set up so that we have a bunch of pixels here sequentially on this side of the screen. Only did the first half in order to test, and then was going to sort of move that over to the second half. And these first bars here are actually written in during VBlank before the frame actually starts, and that was the test that we could actually write through the right ports and the right registers. And then later throughout the frame, it's trying to write to VRAM as the frame scans down, but it's unable to do so because we're locked out. So that's what this is. So we got to change a bunch of stuff. We got to change the video mode. We got to change the way the graphics are laid out in that video mode. We got to change the way that we write stuff. And yeah, but at least we know that this method should actually work because we've actually seen it work, not like the other times when I said it should actually work, where I was making some incorrect assumptions. So yeah, the first thing I'm going to do is I'm going to remove this clear VRAM loop because it was much easier to see stuff going on here when we actually had some random data in VRAM. Oh. Emulator's having trouble starting, apparently. Not sure what's up here. Okay, don't know what happened there. There we go. Yeah, so we still have this sort of stretching thing here. Like this, it makes it very obvious to see that we're stretching the pixels. But I've only populated the left half of the screen. I'm gonna probably keep it that way for a while, just because this was a good test. We're gonna do a few things differently. First of all, I'm also going to remove the dummy writes that we have there, because those aren't actually helpful in this case. These. Get rid of those. Oops. Yep, things still work. By the way, this dark part of the screen, what I do is I change the screen fade register when I start drawing out the HDMA tables, or start filling in those tables, and then when I'm done, I change the brightness back to normal. So this is basically the time, in addition to the time spent in VBlank, that it takes populating those tables. And it's fine that it starts displaying out of those tables before it's finished populating them. As long as the values are there before the specific scan lines that the hardware tries to read them, then it's going to be okay. And even if they're late, it's not going to break anything. It's just going to be glitchy. So not a huge deal there. But yeah, so like basically the first thing we want to do here is I'm actually probably going to disable. So I'm going to first disable the writes here. And then this is set up into channel 1 here. So we can just write 02. And then we should still get our scaling here. Oops, wrong comment syntax. Yep, so all that works as expected. And I'm actually going to disable that as well. So this is basically just what we get here in VRAM. Actually, you know what? I will put that back. The reason being that at least it sets it to initial value. Actually, why don't I just do that instead? Let's do that. I think I need to write twice to the scroll register. Let's do that. Here's our VBlank. Let's just make sure I did turn that off. Yep. And the graphics data that we're writing now, it just ends up being down here, and that's why I want to reset this to initial value. Eventually, we can take this out when we get everything hooked up again. But I'd like to see the graphics as I'm filling that out, so that'll be helpful, I think. We Yeah, so I think it should just be, actually we should just be able to do STZ 210E twice. Except I actually think that that's 1 pixel too high. We need to do this here, store A here for the low byte, and then 0 for the high byte. There we go. So now we see this row of red pixels here at the top of this first set of characters is the data we populated. But it's the population itself is gonna end up being quite different when you switch to mode 7, and that's why I wanted to set this up like this, so we kind of have as much control over these parameters as possible before we start changing that, because the data in mode 7 is not laid out in bit planes like it is here, so we're gonna have to do some funky stuff. Another thing, this says clear the character data and then upload the characters to VRAM. So another thing that we're not going to need to do here is this, actually. VRAM is going to be static, and we're going to clear the color data, actually. Now, I think this is the only place I actually write to VRAM right now. I am pretty sure. Let's just comment this out. Yeah, so we still get the, like this would have cleared the tile data, but we still get the screen data that points to those tiles. So that's why we get at least similar colored stuff here, because they're all pointing to the same palette. And that's the stuff that we're going to have to change here. Now, I think I'm going to set mode 7 first before I dig into how to change that specifically. I don't quite remember the format, but I've got documentation open here. So we're going to set graphics mode 7. Oops. Pull this over here. The 2105 is our screen mode. We want mode 7. Now, I'm fairly certain that all this like tile size and stuff just does not apply to mode 7. I'm pretty sure it's always 8x8. I could be wrong about that, though. But I don't think I am. Mode 7 has only 1 BG. Yep, that makes sense. I also have additional bits in the scroll registers for mode 7. Not going to worry too much about that yet. Mode 7, both the tile map and the tiles themselves are stored differently. In fact, the tile data and graphics data are interleaved, and I'm pretty sure this is done for easier random access by the video hardware, as it's translating the pixels and not necessarily reading them linearly. First byte, low byte is an element of the tile map, and the second byte, high byte, is the color value of a pixel. So basically, we need to write every other byte for the pixels. But we're probably going to have to think about how this is laid out in memory here. In fact, I may set up no cache as the emulator I'm using here again in order to make this a little more visible, but we'll see. Mode 7 screen occupies all of the first 32K of video RAM, 60K graphics data. The other thing, tile map format is simply the tile number with no other information. It takes 1 byte. Dimension of the tile map are 128 by 128. Unlike all other screen modes, the graphics data is in a packed linear format, and each color value directly indexes into CG-RAM. The tiles are still 8 by 8 pixels, and thus take 64 bytes per tile. And there are 256 characters in total. The calculation to find which character to display is simply 64 by the tile number. So I think actually it makes sense then. I have to think about that, actually. I was trying to think about why the other intro did it sideways and why that would be easier. And I guess because then it would write a couple bytes of data and then skip a bunch of bytes, and then write a couple bytes of data and then skip a bunch of bytes. And you could configure that skipping of bytes to work out so that you're always ending up writing like the first pixel of a scan line and then into the next tile or something. Not entirely sure there, but for us it doesn't really matter because I want to just do it horizontally. I think that'll be probably a little simpler to wrap my head around at least. So for the tiles, I think what we're going to want to do is basically the same setup that we have here. But first, actually, there's a couple things I want to do. So I did change this to mode 7. And I just want to see what we get here, because one of the things that I'm a little bit concerned about with using mode 7 is that we may have to reset the scroll registers, or the matrix registers for mode 7. I just want to make sure that if we don't have to do that, I'm not going to do it. Also, I didn't actually change the graphics mode, so that might help. Yeah, we probably have to do it. We'll see, though, because I think one of the things I can do here is if I clear out a bunch of, like, the beginning of memory. Like, if I clear out half of VRAM, okay, that's actually a really good sign. Oh, well, actually it wasn't, because I just remember that half of VRAM is gonna... I want half of VRAM that mode 7 takes up. So that's not necessarily a good sign. I want to clear just a bit of this data. In fact, let's even do this. See how much we need to clear before things get very red. Ferris makes noise textures. Ferris becomes Finnish. So what I'm trying to do is see that if I just clear some of the data, that we'll get like half the screen cleared in like a deterministic way. I'm a bit concerned, actually, that this is so weird. Yeah, okay, it's just being non-deterministic. Yeah, so that to me says that we need to set these mode 7 registers. So I need to look those up. In particular, it's going to be the matrix registers that we need to set. Okay, does this not have those? Say matrix. No, they're not here, I guess. So I'll look elsewhere. I feel I forgot to close my window. But whatever. All right, so we'll just pull up something here. Okay, yeah, so we need to set 211A. By the way, was that in here? 211A? Okay, no, it's just an example for HDMA, but okay. So we need to set the mode 7 settings, screen out settings, and screen flip. So we're gonna just set these to 0. Just have it repeat the screen. So what this is, by the way, screen out settings, is that there's like a 128 by 128 tile map that you describe, and the stuff that's outside of that, so you can scale and rotate the background so that you end up drawing a bunch of pixels that's outside of that region, and it determines what happens inside that region. So does it just display the color 0, or does it repeat the screen, or does it take tile 0 and just repeat that forever? And depending on your use case, all of these could be very useful. I'm just going to set screen repetition because that's going to be zeros and not care about anything else. We're going to have it set up so that we just have 256 pixels across anyway. So we shouldn't, I think 128 by 128 tiles is 1024 by 1024 pixels. So we're never going to use all that space anyway. So we don't have to care about it. And then we have screen flip, and we're going to do no flip. And if I recall correctly, I think the screen flip applies to this stuff still, but I could be wrong. Maybe it just flips the whole thing. No worries. Anyway, should just be able to set 0 here. Let's just see here, 211A. And then we need there's the center coordinates. Now I think we can actually end up setting the center coordinates to the top left of the screen. I think we can do that. And then we'll set these up for that. Here it even shows our identity matrix. And this is scaled 8 by 8, which means we're going to put, if we want 1, we need to put 1 in the high byte and nothing in the low byte. Should be what that means. So I'm just going to start writing 0 to this. We'll see what happens. Maybe that helps, but we probably still have to write the matrix values. That was a coincidence that we got something sensible. Still noise textures, and I'm sure it will be until we get most of this stuff set up. So the reason why that's not non-deterministic is, I guess, the hardware state has been determined to be, like, generally, hardware state is non-deterministic when you start it up anyway. For digital circuits, like, that's just a physical property that they have. So typically you have like a reset line, and there's usually some analog circuitry that will hold the reset line for a certain period of time. And there's going to be some logic internal to the chip that when the reset line is high, that it's going to set a bunch of stuff into initial values. And then when it goes low, then it will start its normal operation. And a lot of these kind of registers, sometimes they're covered by that reset logic, sometimes they're not. And I guess in this case, they're not, and at least that's what the emulator thinks. So that's why they're super random. Really common for especially memory contents to not be cleared, because that would take many cycles to actually do. And the way that this reset stuff works, you're usually not getting a clock. Sometimes you will get a clock during the reset period, but not always. So it doesn't really help. Like you'll never have multi-clock stuff during reset unless that'll usually begin at like when the reset goes low again, it starts getting clocks. Then there's going to be like a startup period as well. But yeah, you don't clear memory with that. I imagine you could, but I've never seen anything that does that. Okay, so now we need to set up our matrices here. So where are the... Okay, yeah, so it's A through D, 211B, and 211E. And it's giving us A, B, C, D here. So A and D we want to be 1, and then B and C we don't care about. So 211B. Let's try this. I think we store low byte first. And then high byte. Is this typical? we're going to load A with 1, and then we're going to, yeah, this should work. So should just need to set zeros for everything here, and then do D the same way we do A. And I think that makes sense. And then still getting random stuff here, but there could be a number of reasons for that at this point. Let's see if I missed anything here. CD. That should make sense. Okay, let's try to clear more stuff here. Also, these tile location and char location things don't matter. And there was another thing as well that the we had in here, mirror of the character memory in RAM. We're not going to have that anymore because we're just going to be able to write a bunch of sequential values to draw the bars when we write into the color memory rather than having to read, modify, write from this memory. So that should make a lot of sense. And yeah, I wanted to clear more stuff in this loop. Hey, middle voids. So the thing that's kind of concerning me here is that I'm expecting something like this, but straight. And we're getting stuff all over the shop. So what am I doing wrong here? Also, this is going to be different, but I'm not too concerned about what's in the palette for now. Yeah, there's clearly some rotating and scaling going on, but I set these matrix. Oh, okay. This is what it is. I didn't change these register values. Okay. This is at least more what I expected. And if this is deterministic, then that's actually a good sign, but I feel like it's weird that we get these random ones filled in. Maybe it's not, but I'm pretty sure it is. But at least now the rotation and the scaling seems to be deterministic, which is what we wanted by resetting those values. And maybe what's showing here is also correct. Let me start clearing more of this memory, and then we'll see what happens. Okay, that was apparently a lot that I just cleared. Actually, let's do that again just to make sure nothing crazy is going on. Do halfway there. Because I'm only yeah, okay. This is more what I expected to see because I'm only clearing the first in this case. I don't know what fraction that is. First bit of video memory, and then the rest just ends up being whatever it ends up being. But this actually is kind of what I expected to see. So I'm basically clearing the first whatever tiles that's covered by this memory range, and also the first tile indices that are covered there. And so the red blocks you see here are this is places where I haven't touched in VRAM, and it should be displaying tile data from VRAM, but the tile indices here are pointing to indices within the range of data that I've actually cleared here. So this makes sense. In any case, the value of what we've done here, though, is just set up mode 7 and set everything up to be, deterministic here. But what I want to do is actually fill in the tile data with meaningful stuff. So I'm going to do that. Now this load tile map, we're going to get rid of because it's going to look different anyway. Yeah, and there was a clear character data. I'm actually just going to get rid of this whole thing. Not that, because I want to adjust that. This I'll adjust as well later to clear the palette, but we can deal with that in a sec. Make sure we're still good. Okay, now I'm actually not going to clear VRAM. I want to keep this around. But we shouldn't need to do it. Yes, we're going to set up. We want to set up the character data, or sorry, I'll call it the tile data and the map data. And we kind of got to worry about one and then the other. So we need to think about how this data is going to be laid out. So one of the ways that's probably fairly easy here. So each tile is 8 by 8, so it's 64 bytes. So we have to write 64 consecutive bytes into the. Let me go up here again. Mode 7 graphics format. Mode 7, but the tile map and the tiles themselves are stored differently. Yeah, because they're interleaved. The first bytes are going to be the tile number, and the second bytes are going to be the graphic data. So we need to basically write the first 8 pixels of each tile. Now what I'm thinking is I could probably just write that out 8 times. Like, okay, I probably want to do this in 2 loops. One where we only overwrite the first bytes for the tile numbers, and then one where we always write the second bytes for the graphics data. Now the tile numbers is probably going to be a little bit easier to start off with, just because it's going to be linear, and basically we're just going to write the first byte of these words here. So I think that'll be easiest. Now I do want to check 2115, whoops, which is going to be, yeah, video port control, because we want to do this increment by 2 bytes here, and I want to do it on the first bit that's stored here. So we're going to do this. It's going to increment by 2 bytes. So this should totally work. So then all of our, if we just write a bunch of 8-bit values, then this should work. So we'll not do this. And do this. Or start at the beginning of memory. And 2d6/8 is 32 tiles. So we'll write 16 at first, because it should be easier to see that the first 16 are correct and then the other ones aren't. And then we'll be able to bump that up to 32 when that works properly. And so here, we should just actually be able to write X here. And then because of this port setup, then it should increment the values like we expect, and it should work. Hunter, is it faster to load value into A and then store it into memory than to store the value directly? As far as I know, in this instruction set, you have to load a value through A and then store it in memory. In this case, it wouldn't be loading into 0. I could just do 0 here, but 0 is a special case in this instruction set. The instructions don't allow you to just say like store 6 into this value, so you have to go through A. It would be faster for sure if the instruction set let us do that, like it does with x86 and some more modern instruction sets. Most RISC instruction sets don't allow you to do that, but that's more of a design philosophy. So I would say generally no, but we don't really have a choice. Now, what I'm actually going to do is I'm actually going to store 0 here, I think, for the first 16 tiles, because what I want to see... Yeah, okay, here's precisely what I wanted to see. A bit subtle. Let me do this. Or maybe my eyes were deceiving me. Because now I seem to have lost it. Maybe I was seeing something I thought I was seeing something that I wasn't. But what I'm trying to do here is set up the tile data. Actually, this is the map data that we're setting up here. And then we'll do the tile data. What I want to do is I want to have the tiles set up so that they're just increasing in memory. But in order to see it and see that it's working, so we can kind of do this incrementally, then I'm just going to store 0 into all those, and then we'll put some deterministic data in the first tile there, and that should work out. So I'm going to do basically copy this. For now, just clear tile 0. And this will be 64 bytes. And we want to store to 19 here. And then we're going to want to put 80 here. And so then we'll write the second byte of each word for 64 of those. And that should be our first tile. Yeah, tile data loop is already defined, so we'll do... Actually, this is going to be map data loop. Okay, so it looks like we at least were able to clear some of a tile, not all of one, actually. Looks like it was cut short a bit, which is not very good. As we want to increment when 2119 is accessed, and we want to increment by 2 bytes. Let's just see what happens when we run this again. Yeah, it's just getting a bunch of random stuff. So what I'm hoping to find is that we see a bunch up here. Now I'm wondering if we have to set up our center coordinate in a way that I am not expecting, which may make sense here. And if that were the case, then we would want 128, 128 for the center chord, I guess. Or we would want 128 horizontally. Vertically, we might want something different. Well, we could just try this. In this case, we want to store that as the low byte, and then the high byte's going to be 0. gonna put that back. It's a bit strange that we're only writing half the characters here. That's not what I would have expected. And that should... Yeah, shouldn't change that. Let's see. See if I make this a lot higher. Oh, yeah, of course I need to use a 16-bit index register for that. Oh, wait a minute. I never reset X here. Okay, so now it's writing at least the full tiles. So I'm guessing that this is working now. But this is still not writing what I would have expected. Let's write a bunch more data. It seems like we're just displaying a bunch of random stuff here. That's not ideal. Okay, so there it looks like we wrote all of this over. Yeah, so this, if I turn this to 20, then we should be getting a bunch of half tiles here. So that makes sense. So this is working properly, at least to clear that first tile. But the map data is still not writing what I would have expected. I kind of want to see where I don't see this anymore. So it's, how many tiles was this again? 128 by 128? I don't think the stream's down. Which I'm happy about. So each time I do this, like if I do 1080 here, that should remove one of the rows here. Yeah, remove entire rows. So that means if I do this, right? So that's 4K over 128. Uh, 4096 over 128, and we have 32. So I'm 32 rows off, which is 256 pixels off of where I would have expected to be drawing. That seems a little odd. Seems a little odd. Actually, you know what that probably is? Probably my initial scroll value. Yeah, okay, that actually makes sense. So the scroll value was set to 255, which when the graphics was when we were using mode 0 and we had the first background to be set to 256 pixels high, then setting it to -1 would have wrapped around. So we would have gotten the first line like we would have expected there. But in this case, that's not going to work, it looks like. Now, the problem with that is that I think we're still going to be 1 pixel off when we actually try to show this. So we're going to have to... actually, I think all we have to do is set the high byte there and just actually make it -1 in 16 bits rather than 255, which is what it actually was when we did that. So maybe if I just do LDA FF here, then we can store this into both. That probably works. Yeah, then we get the same thing. And that's good. And I bet if we do, no. Let me just reduce this instead now. Yeah, that looked like it worked. Let me go ahead and set this back to. And I think this will work now. Now that's 128 tiles. I think we only need to write 32 of those. If I write 16, we get half the screen. Good. So now our data layout is actually starting to make sense. Good. Also, these tiles do look a little fat. And the reason there is I don't think it's that we're writing them wrong. It's that the pixel aspect is not actually 1:1. It's slightly wide. I bet there's settings here to change that. Like if we turn off aspect correction here, then we get square tiles. So that makes sense. So yeah, so if I write 20 here, then we're going to get our at least zeros for our whole map data. And then if I go... Actually, if we do FE here and FF, then we should see 1 more pixel above those as well, just to be sure. Yep, good. Okay, things are acting predictably. Always a good sign. It also means that we're going to need to incorporate this high byte here when we do our scroll HDMI channel. That may cause us some problems. Maybe we're okay, though. Yeah, our initial Y value here is FF. If we do that, it probably works. In fact, I can test that now. If we take out our reset here. Yep, and then we'll get that somewhere. That's fine. And then we set up the scroll HDMI and we just turn that on. I think it should do that. And there we're getting some stretching. Now I'm pretty sure this is going to be the first pixel. It may be 1 or 2 off, and we're going to want to tweak our data to figure that out. VTimKS says on Amiga we used to use the negative modulo trick. I am not aware of this trick. What is that? What I'm going to do also here is I'm going to set this so that here we clear the tile data. This is writing all 64 bytes. I'm actually only going to write the first 8, which that should give us 1 thin row of red pixels here. And then I want to test the stretching. And if that works, then we're really in business. Yeah, so now we got red. So that's definitely what's working there. Now I'm going to leave this. Or actually, I'm not. Because I think it'll be easier to debug what's going into video memory if I don't do that. So now we want to set up our tile data. So instead of storing 0 here, it's actually going to store X. So we get all the tiles in increasing order here. And for that, the first one still should have been X. Whoops, that was the tile data. We want the map data. So we want STX here. And then the first one's going to have a red line, and the other stuff is going to be whatever, because we're not actually writing any data there. Oh yeah, negative modulo. Yeah, so that's almost exactly what we're doing. But we're not increasing by the width of the screen. We're actually just setting a horizontal scroll register to basically do the same thing. But same stretching principle, just display the same line over and over again. But yeah, just to use that is what that was, where it was all red. It was one line being stretched all the way. In fact, if we do what we have here, so we only have the first tile having this red line, and I enable the stretching again, then we're going to get just those left 8 pixels stretched. And then, yeah, everything gets stretched, but the only this part's going to be red, because only that first tile had that 1 pixel thing. So there's our stretcher. Now I want to, the reason I'm disabling it is so it's easier for me to see how this actually looks unstretched, kind of a debug mode, ironically. So yeah, so we want to, the map is now increasing, so each position is actually displaying the next tile. And so then when we write that tile data, we want to do something clever here. So first we actually want to store X here, as we basically want to store increasing pixel values. Particularly, how do I want to do this? Like, so we want the first row of pixels to all be increasing palette entries. So I think I might just use both registers here, because we're only going to end up with 256 of these. And if we just store, like, let's say we did LDY like this, I think we can do TYX in this architecture as well, which is nice. Then we should be able to, let's see, if we can do something like this is what I'm thinking. So tile loop and tile data loop. We'll do that. So we should end up with something like this. Increment Y. Compare Y with how many tiles do we need? 32. And branch otherwise on the tile loop. So we're going to write the first 8 pixels of each tile. And we can always just increase X here, actually. So we can just, or no, because we need to compare it there. I think here's what I'm actually going to do. Let's do this. Let's push Y, and then we'll pull Y here. And then we can do LDY. So basically what we're doing is always storing X into here and then incrementing X. Maybe doing that with A is actually better, because then there's less fiddling. Because then we can do X here, STA, increment A, and X, CBX. So then this is actually going to be, let's do, I always like to load this into A if we're doing that, and then we'll do transfer A to Y. We shouldn't need to do this then. So A is just going to always be increasing as we do this, and we're just going to write 8 bytes each time. But then we need to figure out which tile we write here. Now I'm fairly certain what we can do here is we can push A and we'll pull A after that. So the issue here is we're going to need to add 64 bytes every time for the offset here. 32 when we actually do the indexing. 32 by 32 is going to be more than 256. So we actually probably have to get a little clever here. Let me do this. Let's not worry about the increasing value here for now. Or actually what we can do, this is X. If we just do this, if we make 8-bit A, let's do that, and then we'll do 16-bit X and Y. Then we cannot, instead of incrementing Y here, oh wait, I have to, if I want to add here, I have to do it not through, I have to do that through the accumulator, don't I? Hey, 2bits. So I think what I was thinking here was to basically do store Y here, and initially Y is going to be 0, like this. But then we can do let's just do it this way. Or actually, hold on. Really feeling the register pressure here. This is one of the reasons why this architecture is so annoying. We can do right here. Let's do this. Keep these 8-bit. And what we can do here is let's do 16-bit A. So first thing we're going to do is we're going to push A, and then later we're going to set it back to 8-bit, and then we're going to pop it. And then when we have 16-bit A, so we can push A, and then we can do transfer Y to A. And then we'll set this to 16-bit A. And we'll go ahead and that with 0FF, so we only have the low bits. And then we can multiply it by 64 by shifting left 4 times. Six times. So it's by 64, but we actually need to divide that by 2 when storing here. And then this becomes STA into 2116. I think that might be it. Didn't like ink, so it's probably ink A. So we're getting some stuff down here, which is probably not what I wanted. I tell you what though, what I'm going to try to do here is STX. So we're just going to write the same 8 pixels over and over again for debugging. And what do you know? There we get, that's actually, that looks correct to me. One of the things I also did here is I think we're still, oh no, we are writing the whole map data here? Okay. Then why? Writing 32 tiles worth of map data here, and then 32 tiles worth of tile data, but somehow Somehow it didn't seem to cover the second half. Maybe I'm not seeing that right. Yeah, like halfway through it doesn't seem to be correct. One of the things we can do here is I can write this out more times. We do 64 here. You didn't know what this AAA project is? I don't want to tell you. Now, actually, I think what that was is that was one of the test servers I did when doing switch hacking. I think that was all that was. Yeah, that's what this was. Not that exciting. All right, well, maybe it is. So now we're writing 64 bytes of all these. So it makes sense that we're seeing this, for example. But why does it crap out on the second half? I can try doing ASL here again, and I expect that to write every other tile. Or maybe that was correct. That's a bit odd. Because 6 shifts should be correct for multiplying by 64. Oh yeah, of course, it's 64 times 2 because we're only writing the first byte of 2 byte values anyway. So it's actually 128 bytes that we're stepping, but we need to shift it left by 6 to multiply it by 64 because the value we're writing is the actual value over 2. That makes sense. Okay, so let's just write the first values again. And then our top row should be the same thing over and over again. And now if I do STA here, we should basically be displaying the palette as the first row here. Now we've only actually written the first few values of the palette, and so I'm going to do that next. In this case, we can just do increasing values for now. So we could do, for example, so everything's 8-bit here. Let's do this. Store 0 into 2121. And we'll do this. The TAX, increment X until it wraps around. And here we can do STA and then STZ. CC80C, don't need that stuff. Actually, we want STX here. Don't need A. And this should give us a bunch of red that wraps for the first row. And that's what we get there. So for example, if I enable the stretcher again, also everything turned red because we write out the whole palette now. That's what that was doing. For example, if I did this as 80, we'd write the second half of the palette. Okay, yeah, so we actually do write the first half of the palette, yeah, because this was the index, and then this just writes out from there. Okay, so that makes sense. But we do want to write out the whole thing, and then if I enable the stretcher again, we should be well on our way here. And then we get these bars here. And this is exactly what this should look like. So that's good. This is actually going quite smoothly, but that's probably because I was thinking about it throughout the week. So let's screw this now because we don't need that. We could clear VRAM, but we don't need it. Now, what we actually want to do here is instead of setting up the colors, we actually want to clear the palette. Bars hype. here's what we do. With the vars, do this here. So we actually want a clear palette. And the way we do that is just write 0 the whole time. So we store 0 into the palette index, and then we write 0 for 256 bytes. Write it twice because each color is 16 bits. And then we'll branch out of the palette loop. And now we get black, which is what we wanted. This will be some greenish blue thing. Yep. With weirder bars because everything shifted in that byte, which is why it made more sense to test with red, because the lower 5 bits will just be red. So that's nice. And a little bit of green as well, because it does end up, if it's the lower 5 bits, then we also get the lower 3 bits of the green. And so that's why it gets a bit yellow over here. So looking good. We actually do want that to be black. And then what we're going to do is some magic stuff here. So we want to set up both HDMI channels. Now I'm pretty sure this first one, I still have the table set up to just do video RAM updates, which will totally fail. But we want to enable that again. And things are going to get a little bit different here. Oh, I bet Metal Voids. I bet you knew all along. I'm going to reorder these again. Because I think we're going to end up using multiple HDMI channels to actually write the data when the time comes. And it's going to be easier for me to get the scroll one out of the way and then do the other ones. Now, currently, I have these VRAM adder and data ones here. I'm going to set this up, by the way. Set up CG RAM data HDMI table. So all says VRAM, it needs to be CG RAM, which is the color graphics RAM. Terrible name for that. Now, currently, I think I had this set up to write out 2116 and then 2117. And then 2118 and then 2119. So we're using an HDMI channel mode that basically writes 4 bytes to successive registers, to 4 registers in succession. And I don't think that's going to work for the colors because we need a 1 byte write for the address of the colors, and then however many writes that we need to actually write the data. Now, the easiest way to set this up is probably to set up one channel with the addresses and another channel with the writes. And we may actually get away with using multiple channels for the writes to get extra wide bars. So, yeah. But we'll see. It's going to be easiest to set it up to just like write one value to start off with. But anyway, this table here is going to be crap. This should be CG RAM. And I bet, yeah, we had this. Instead of the address and data table, let's just do the address table. We're going to do another one for the data. So we're going to use one channel that's going to write out all the addresses, and another channel that's going to write out all the data as different writes. So it's going to be the address here, and this one's going to be the data. So we're going to have this in an increasing HDMI channel index. And there's going to be some stuff here that I need to do. So for this should be the same as this one, because we're just going to write, actually this writes 2 values in succession. We actually only want to write 1 value in the case of the color register. Yeah, sorry, CPT, I have links disabled. So let me pull up Grog's guide. I think it was here. Yeah, this is what we want to look at. I can't see the link, CBT. So, yeah, we want to just write 1 byte here. So I think we just need 0 there. And then for the color, we're going to want it to write 2 bytes to the same register again. So we're going to write 2 to the other one, 2 here. And that should work. And then we want to write 7 to this, which will be the lowest 3 bits to set up all these running. I actually want to set up both of these in the same loop. Or actually, I don't, because the indexing is going to be slightly different. So let's do these separately. This will be the address table. And then we're going to do the data table here. Now, one thing we can do here, I don't think I need to switch to 16-bit A for this. And we need 224 by 2 because it's going to be the repetition index and then the value. And we can actually just do, for starters, we can do STZ here. That should work. Yeah, so we're going to store 1 into the repetition index of the table, and this here for this many entries. So that should make sense. And we do the data. The data should be by 3 because we need the repetition index and then the value. And for now, we can just hack this, make it white. There's some extra bits here, but that's fine. In fact, there. Now there's not extra bits. Now, I would have expected that to give us a white line down the left of the screen. And it didn't. Actually, here, let's do this also. Let's do a little bit into the screen for our address there. Oh yeah, I also didn't set up the register indices right, did I? Yep, that would do it. 2-1 and 2-2 here. And there. Holy shit, guys. We finally got per pixel writes here. Or per scanline writes into the palette. So what I want to do now, so this was our index. Actually, what we want to do here is we have our bar pause. And this is actually what we want to use here. So we have our address table, and we can load A from the bar pause, store A there, and then we'll increment bar pause for that table. And there. So this basically works. Hey, Hex Pointer. Well, I'll see you later, CBT. So what's happening is that it's drawing one color into the palette. This is actually totally correct. It draws one color into, or it draws like our bar is one white pixel now, and the position just increments every time it writes one, and then it'll wrap around. So this actually makes total sense. We need to have a sign table for it to do the writes properly. But before that, I actually want to do adjust the writes that we're doing so we can actually get some additional bars here. Particularly, one thing that we should be able to do is we have it set up now to, in this case, write 2 bytes here. And I actually, is there a possibility for us to write 4 bytes to the same register? I don't think there is. No, there isn't. So we actually need to use additional HDMI channels for each of the additional widths of the bar, and that kind of sucks. But this is totally working, by the way. This is I'm quite happy to see this. So if we write, let's see, how do we want to do this? Oh, also we can get this to move. This is moving too fast, so we actually do want to change that. So this is our bar position here, and then we'll do another RAM thing here. Bar pause temp. There's a reason why we need this. So ink bar pause here. And then we'll use bar pause temp. So we're not just writing to that the whole time. There. This is more accurate, at least for speed, but it's the same idea. So now we can set up some additional channels for the bars. I guess we can only have 6 pixel wide bars in this case. Unless... Oh no, because for the color part we have to write out values for that. Yeah. Yeah, unfortunately this is the only way this is going to work. If we use multiple channels for these. That's fine, because at least it'll be straightforward. Let me adjust some of these table addresses here. Let's do 041014. Let's put 18 as well. Call them data 1 and data 2. Now I shouldn't actually need this much data, because this is a kilobyte for each one, and we should actually only need about half that. Or in the case, if it's 3 bytes, it's 224 by 3. Plus 1, actually. So 673. So actually it's pretty good to use this for a little safety net. So let's keep that. The unfortunate part, of course, is that... Well, actually, I guess I could just access this through a different bank, and then we have additional memory to do this with. I'll probably do that next. Set up another channel here. Data 2. And it's gonna write to the exact same stuff in the exact same way, exact same registers, but because the HDMI channels are processed in a deterministic order, these will happen after these. So basically this is going to be the first color of the bar, and this is going to be the second color of the bar. And so the first one was white. We can do white on the right-hand side, and then on the left-hand side we can do Yeah, not white. We could do like half, which will be, I'm not sure what it's going to be shifted. But it's, so 31 is our 5 byte saturated value. So 15 should be, have that, or we can do 16 in that case. Left shift 5 or 16. Left shift 5 or 16. And we'll get 4210 for that. Now, it should have written both of these, so I'm not entirely certain that this worked correctly. And it's probably because, did I change the pointer here? Okay, I did. I didn't change the lane here. The channel index. Yeah, stuff I say is deep. So this makes sense, but I'm not seeing the edges of the bars like I wanted to. So let's go ahead and, for the address, let's increment this twice. And then we'll see that this is actually bars. If I increment it a third time, then we'll see some space between the bars. And then we'll get something like this. But I think we're ready for a sign table now. To actually make sure this is working properly before I add additional colors or anything. But guys, this is actually working. And we will totally finish the effect today, and that's nice. I'm gonna just commit this. Yeah, dithering horizontally, or sorry, dithering vertically will like be hard. Not gonna do that. Dithering in terms of the colors horizontally, it depends on how many colors we get. If we have to use an HDMA lane for each one of these, we should definitely have enough memory to do that. But we're only gonna have a 6 pixel wide bar, so dithering may not make that much of a difference. But yeah, Hardcore Head 87. Why is the top half darker? That's an indicator that I have set up. So I make the screen dark, and then I do all my processing for the frame, and then I make it bright again. So that's basically saying that I'm taking up half the frame in order to do all the processing that I'm doing. It doesn't need to be dark. It's just like printf debugging kind of. Yeah, so let's build a sign table. Now, I don't think this assembler can do it, but I can just make a little Rust project that does that. We'll just import it as a binary. However, thinking about where I'm going to put this in memory. Or I guess it'll be at a ROM, won't it? So it doesn't matter. Yeah, okay, then I can just build this. Yeah, so I'll make that. So in our SNES Kefrens bars things, we're going to do cargo, new, bin, sign tab. And I could sit here and make this nice with a make file, but first I just want this to work, so. Get our stuff, and we can just do a very simple 256 byte table, and we'll make it more complicated as we go. Yeah. I think we'll do something like this. think that works? Yeah, and then of course we didn't actually have the value there. Yep, okay, good. I think actually, by the way, I will set this up with a makefile. Because I actually don't think it'll be that bad. We can do... Let's put some of this up. Yeah. We can just do this. I should call that like syntab gen or something, but that's fine. Let's do tab. That probably works. And then for the objects, we can do source and the tab as well to build that. And that should work. And then I think we just need ink bin or whatever for WLA. So it should just be I guess we can do it here. We can make another section for this. Right, and now I can't find tab.bin, which makes sense because this didn't actually generate anything. Good. So now we can do just do this 0 to 256. We can map each of these. And then we can collect that into a vec. And then we can do output. Output dot writes all and bytes dot unwrap. And then here we can do I as f64 divided by 128, because we're going to go to 2 pi. I think we have pi in here. Yeah, we have in. Use SCD F64 const pi. Right, so this would be or you can call this. I usually call it F. I don't really know why. Then we can do F dot sign times 64 plus 128. And then we can take that as U8. And that should be a basic sign. And it didn't like that I didn't make this mutable. And there we have a sign table, but it's not being used. I really like Rust. And just like how quickly it was for me to just set this whole thing up, and like now it's working. That's kind of the real value there. I mean, granted, something like this could have also been done very simply in C, but you know. So now we have our tab here. We can do sign tab like this. Stick a label on it, and then we should be able to do something fancy like this. So if we do, so instead of doing A here, I actually do want to use A. The unfortunate part is that I'm going to do some indexing with one of these registers, but they're 16-bit here. But I can do this. Let's do this. So do 8-bit XY, and then we'll reset that in a sec. Like that. LDA from the bar position temp thing here. That should work. Something went weird here. What the hell? I don't know. I don't know what was wrong with all the colors and shit. Judging by the fact that it's all dark, we may be taking too much time per frame. There might be some shit there. Our sign table worked. Yeah, so one of these values, 8-bit Y, so I can load this. Load the sign table offset by Y. So we have the value in A, and then reset this to be 16-bit, which shouldn't truncate the index registers. I wouldn't have expected it to, at least. But why would this have taken that much longer? I mean, this indexing then does take longer for sure. Like, let's say I do this and not this. Does that make any difference here? Sign tab is too much to be an 8-bit value. I'm not trying to load it as an immediate. I'm trying to load it as an absolute value. Why is it giving me issues there? Not sure, but if we do this. Okay, so that already screws something up. I wonder if we're just not supposed to. I wonder if this does truncate. I really wouldn't have expected it to. Need to look that up, actually. We're close, guys. Oh yeah, no, I'll totally finish this today. Gotta figure out why this is. The bars are still gonna be pretty small when this works, but I don't think that's gonna matter much. Okay, here we go. One important difference from the M flag is that when the X flag is 1, the XH and YH registers are forced to 0, so that actually is exactly what's going wrong here. That's kind of a bummer. Although, I can do this. I can push X and then pull X. Not going to be the fastest loop, but I would expect it to still be fast enough. So here our loop's fast enough, but it just looks super jank. Strange. Wonder why that is. 30 space of memory left for some lobster bitmaps? Oh, there is, but we'd have to display them as sprites. And that would be annoying. So I'm not going to do that. You know what I actually want to do? I want to remove that bar pause temp thing. We don't need it. Oh, that's why, because I'm loading dir. There we go. No, this is definitely not less than 256 bytes. It's going to be several bytes more, but I could not care less about that. So there the effect is basically working. I'm going to add some flair to the sinus now. F times 64 plus, let's do F times 3 times 32. And that should have... I don't think that ran the sine table thing here. Hold up, I need to check another makefile that I have that does something like this. Just to put this together enough. I think actually this is because I think I know why this is actually. Actually, I think we'll do this. I think it's checking for the existence of that folder, and it always finds it, of course. Let's just try that. Yeah, there it ran. That's not what I expected that to look like at all. Oh yeah, because I need to do sine here. That's more what I expected. It's not actually running slow. It's just only moving through the table fairly slowly. There's a pretty easy way to fix this. In fact, actually what I think I want to do here is instead of adding sort of the sine table flair there, we'll do a couple different sinusy things while building the table. Let's see, how can I do this? We're gonna get cheeky here. I also don't care if I get this so where it basically takes up the whole frame. As long as it's working. But in particular, I want to push Y and pull Y here. There's a good reason for that. So I'm going to transfer Y to A. Oh shit, do I need it in... I can actually just shift it left twice. Let's do that. ASL, ASL. TAY. Like this. Yeah. And then we can pull Y there. And then clear the carry and add syn tab with the actual Y. And this will give us a couple octaves of sinus. But But now, because now it assumes that there's no bias here, so we're going to want to do this. And the other thing we're going to want to do is when we load A here, we're going to want to shift that right. And then that should make sense, but then we want to also add our bias here. Yeah, I should just actually use a couple different pointers. That's going to be easier than what I'm trying to do here. But I still don't think that this was correct. Let me try something here. Yeah, so that makes sense, except that it's a lot wider than I would have expected. So add this, add this. Oh, right. No, that actually does make sense. Put the spec down to 64. And that should be correct. And then if I bring this back. I wonder if we're just wrapping a lot here. Oh, actually, you know what? Also, the shifting isn't going to be... Yeah, I'm just going to use 2 pointers. Hey, thanks, Jura. See you, Metavoids. But then this, instead of having LDY here, actually, we still are going to want that. Or if we have 2 pointers, I can just not have Y running through this, and then we don't need to push it or pull it. Let's do this. Do this. Maybe we can even make that go the other direction. And then we can do LDA. And there's a little bit of extra stuff here. So like I could just store this into both of these, but that's fine. Actually, I'll do that. Let's do that. Okay. Actually, crap. This is not what I wanted to do. Actually, this will be fine. This will be fine. Also don't need to do this. Yeah, it'd be easier if we do this, I think. Or no, we'll just load Y from this one. Load A via Y there. Shift it right so that that will have less of a contribution, although this needs to also affect the carry properly if we're going to shift it right so we have the right sign. So we actually need to do ASL sign into the carry, and then we can load it again, and then we can rotate it right, which will make sure we have the correct sign. And then we can load Y with bar tab index 1 temp, clear with carry, and then add it to that other value. We don't need to increment it. We do need to CLC ADC 80 here, and then we can store. There we go. I'm getting not shit at 8-bit arithmetic. Yay. So finally, we got this more or less working. I do want to do a couple things with this, though. One thing I'm a little worried about is how long we're actually taking per frame. I mean, like we're clearly beating the raster because this is actually working. But if we're gonna add it like another bar, then I want to kind of reduce this. Now, the easiest way to do that, honestly, because we're just taking up just raw CPU time building these tables, is we can up the clock rate of the CPU. Now, the SNES, basically, all we're doing is we're not actually upping the clock rate of the CPU, but we're we're bumping up the clock rate that the bus can handle. And I've never actually done this, but as far as I know, given you have the ROM chips that can actually handle the higher bus speed, all you need to do is execute out of not the lower memory addresses, but execute code out of one of the higher mirrors. Otherwise, you'll get the low bus speed regardless of what this register is set to, and then set a certain bit in a certain register for the bus speed. So let me just look up how to do that. 420D, I think that's the one. Okay, that was actually that useful. Although that was memory mapping, so we're going to need to do some of that. Yeah, here we go. 420D is the cycle speed designation. Either 2.68 megahertz or 3.58 megahertz. So we're going to want to set this to 1. Now, we actually typically want to do this fairly early on here. I think after this is a pretty good place to do it. Disable interrupts, switch to native mode, and then here we could do it. I think that makes most sense. So we're going to do this first. Actually, we can do it as part of this hardware init thing here. So we need to do LDA a 1, STA this. Whoops. Did I lose already? 42D. Yeah. So we need to do a long jump here into basically the same, basically the next address, but in one of the higher banks. And then we also need to do one of these long jumps at the beginning of our interrupts, because the interrupts will transfer execution to a 2-byte value. To the 2-byte address for the handler with 0 in the bank register. So we need to update that as well. Now, I can't remember how to do this. You do a long jump here. Actually, honestly, there's probably a tutorial to do exactly this thing here, but... So jump long is what we're going to do here. And then the next thing we also need to do is we need to make sure we have the right bank set. And then I think all we have to do is long jump and everything should just work. I think this assembler had a support for some kind of relative label like this. Let me see. And then we should just be able to do jump long to there. Now we won't see any benefit from doing it here. Round bank 8, selected bank 128. This is where I get a little bit lost. This is where our variables are. This is where this is. Right, because this is the different ROM banks. So this bank is not what we want to change, I think. Ah, base is the directive. Okay. Now nothing broke, so that's a really good sign. Also, I kind of want to scatter these local labels around in different places in the code, but that's going to be fine for now. So we're basically going to do the same thing here where our interrupt is. So I just want to get kind of a mental note of where this was. So it's down here in like the lower quarter of the screen. And now it's up here. So this totally worked. Evil, yeah, 2 lines of code for free overclock. Most powerful console ever? What is that? It's definitely not the SNES. Yeah, the other thing here, of course, is that you need ROM chips that would have supported that, so a lot of games wouldn't have been able to do this because the cost would have been prohibitive. but the flashcards support it and everything, so, you know. Hey, Jake, how's it going? There's my cousin Jacob, guys. Jake and his cousin Jake. Oh, yeah, the new Xbox thing. Yeah, I'm not hyped at all about that. I'm guessing it'll be cool, but I'm not hyped. I'm not that excited about it. Yeah, Jacob, cool to see you too, man. Just doing some Super Nintendo coding. I'm gonna make these bars a bit wider now. I think this is the bank register. The downside of this, though, is that we need more room in our RAM area to actually fit this stuff. So I think what I'll have to do, actually, I think I can just prepend these with the bank addresses, and then I think the instructions will just work with the 6-byte address or the 24-bit addresses. Should work. Let's find out. Where in that memory map was the upper mirror, though? Let's see, where is this? SNES WRAM mirror. It's over here. Yeah, up here. It's 7E. And then basically all the addresses there are what we want. This will give us a view into what looks to be the first 64K of RAM. And I'm guessing then this bank will give us the second. But we should only need the first here. So as long as I prepend these with 7E, then we should be fine there. Just going to test that to make sure it works first. Okay, so it didn't like that because it was out of 16-bit range. Where's that? 327. Okay, so I guess STZ can't work with that. We can, that's fine though. We can load A with 0 and STA like that. If that is indeed the problem. Which I'm guessing it is. Okay, what happened here? What was that? I should have 8-bit A for all those. Jura says, why PAL? The answer is because I'm in Europe. And I'm just used to making everything for PAL. at this point. I mean, in this case, it should be trivial to change because you can just change the... I'm not going to distribute this as a binary or anything, so just change the flag up here. No, I am an American. I'm just, I live in Europe. And I'm used to making things for European machines now. But why did this change? That was so strange. Now, one of the things that I didn't change, so I also should be storing the bank here. Whoops, did I just close Sublime? Yep, I sure did. Whoops. So instead of storing 0 in all these, we're going to store the bank. I doubt that that would have made the difference here, but it might have. Whoa. Something got fishy. Oh yeah, I need to set the proper lanes here. So what is... Why did that line just show up? What is happening here? Yeah, that's a much needed touch of glitch. Well, first things first, I'm going to make sure that this is actually working out of that top part of RAM there by bumping up these addresses. Do 118.2028 just to make this a little bit easier. Okay, and that still works, so it looks like we're at least addressing ROM correctly there. Or, sorry, the upper RAM mirror. But then what is this? What could that even be? Let's just enable the scroll thing here. Oh yeah, and then we don't get any actual writes. So let me clear that, or sorry, not clear CG RAM. And maybe that helps. Okay, so something is going wrong with this this lane for the scroll register, I think. It has to be because this would this should display properly at least. So for the scroll HDMI, oh, whoops. That makes more sense. When I replace the end addresses of all these, I just wrote to wherever the CGRAM table was. That's not going to be correct. So that would make sense if that overwrote this. Okay. So then things start looking more sensible. So now we can clear the palette and enable all of our HDMI lanes again. Now we're looking good. Okay, so now I think what I want to do is add a couple more lanes. And I'm just going to do it by hand here. Should honestly make a loop for doing this, but this should still work. I'm going to keep calling them Kefrens bars because that's what I know them as. Even though I totally saw the Alcatraz demo that they were done first in, and they were, oh, I hated that demo so much. But it was era appropriate. think after I set this one up, I want to try and putting these in a loop, because this is getting a bit brutal. And it should be exactly the same except for the pointer. Yeah, a couple different pointers and the color itself. I think it was called Alcatraz Mega Demo 3 or something. So we'll do our half brightness here. And then we can do something really dark for the lowest brightness. Something like... So 31 would be our full brightness. And then we had 16 that I put there, and we can do 8. Left shift 5 or 8. Left shift 5 or 8. We'll get 2108. Now our bars look a lot better, just with the third color. But I'd really like to set these up in a loop, and then we can make better use of the last 3 channels, because I'm guessing we can squeeze 3 more pixels into this, and I would kind of like to before calling this quits. And then we can do a proper little color table as well, which will be nicer. But guys, this works. It only took like 12 hours to put all this together when you look at the consecutive time. And the time it was driving me nuts in between the streams, but you know. And I'm actually going to keep the debug screen fade thing going as well, because I want to make sure that we don't run out of time by adding more bars. It's going to be funny if that ends up being our limiting factor, but it very well could be. All right. Another actually kind of cool thing about this approach, by the way, is we can totally do this. Like we can totally just load a color here. 1F. So like if we wanted a red background, we could just do ST A here and only do one of those. And I'm a little shocked that didn't work, admittedly. Oh yeah, because we actually have to write to this twice, so that actually won't work that way. So we need to do, we'll do this instead. But the point is that we can have any background color, and it's not going to affect the bars or anything at all, which is a bit helpful. But yeah, we want to set up this in a loop. And we want to set up this stuff in a loop. And it should actually be faster, because if we do... Well, actually, I'll probably do them as separate loops like this anyway. In fact, the first thing we can do here is drop some of these extra things that will ensure the width of the registers. Now, I think we're not using the Y register, so we can use that as our loop index. That should work. We'll have to do some like indirect addressing and stuff. You know what? Honestly, screw it. I'll just unroll it. It'll be fine. Let's see how many of these we can get as well. We'll just take the same one and repeat it for the last thing, because we are going to be limited here by actually, we need to rename these labels here. We are going to start being CPU limited. Yeah, so this is actually as much as we're going to get away with, is only one more line anyway. So I'll just do that. I'll just hard code it. Doesn't really matter. Yeah. Whoops. Did not mean for that to wrap around. If we had a macro assembler, I would just do this in like a metaprogramming loop, but this is going to be fine. And for this last one, we can do, for the one on the far right side, we can just do we can do this slightly darker color again. Why not? And then all we need to do is allocate some space here for the table and set up the other HDMI lane. Something like that. However, it seems like we missed out on white there. Which is odd. Did I make sure to add extra space for that other table? Yes. It may be that we're locked out again and we missed our window to actually write the value. I wouldn't guess that's the case, but it is possible. It's just a bit strange. Oh, yeah, of course. I see what I did. I did 2F instead of 3F, and that actually disabled the white channel rather than doing that and enabling the next one. So there we have 4 color bars. I wonder if I can make that last one a little brighter at least. Instead of like 16, which is what that was at, we can do something like 24. Left shift 5 or 24. Left shift 5 or 24. I should probably be 6318. I should probably just be relying on the assembler to do this, but at this point I'm kind of in the mood to just throw this together. My goal has been reached, basically, is that we actually got this effect working. So I'm already fairly satisfied about that. But yeah, I think this is basically done. The only thing that I would do now, that I should do now, is test on the actual hardware. Now, I don't have the actual hardware set up, but I do have it within arm's reach, so I could set it up. The question is, will it kill my stream? So here's what I'm going to do. I'm going to push this. So I'm going to push this, and then what I'm going to do is I'm going to set up the hardware, So here's what I'm going to do. I'm going to stop the recording and like end the stream. But then I'm going to turn it right back on and try to set everything up, just in case the stream dies. So I think that's a good plan. So I will see you guys in a couple minutes.